So our objective for today, we're going to talk about Coulomb's law and basically do some more problems like you just did. Then we're going to give you some time to look at the PhET simulations, just clarify some of the directions, and then basically give you work time and time to ask me questions. Just a reminder, we are now on Thursday. So tomorrow your TED number 3 is technically due. So get it done as quickly as you can, get it turned in. I am grading by topic. So I've been going through and grading TED 1, 2, and 3 by topic. So I apologize for how long it's taking me, but I'm trying to put a lot of my priority on that so that, yeah, I get it done. All right, so bear with me on that, but we are making progress. All right, so here we go. We got a set of charges here. We got A, B, C, and D set of charges. We're going to assume that the circles are all the same size because they should be, because I copied and pasted them. So they should all be the same size. Notice that they're not protons or electrons anymore. They're just Q1 and Q2. But which set of charges experiences the greatest electric force? How do you know? So type that in the Pear Deck. And something you can use to help you with this decision is, don't forget your electric force equals K Q1 times Q2 divided by R squared. I like your reasonings. So if you could tell me why you put the answer, then we can talk about it, because we're making assumptions here without actual numbers. We're making some assumptions. So if you can tell me why, that's very important. Oh, interesting. I like it. Okay. So Olivia, I'm going to ask you not to change your answer because I'm definitely going to be using yours, okay? Because you have some really good thinking there, and I want to talk about it with everybody. Okay. All right, let's share a couple of these. And I want to keep in mind that, you know, we get so wrapped up about right or wrong answers, and that's not what this is about. This is about exploring what we're doing and sharing some ideas and thinking about why we would think that, and then talk about what are the assumptions that go into that, okay? So keep that in mind as we look at these. So A has the greatest force because there is no distance between them. The smaller the distance, the greater the force. So that is exactly correct. Letter D, since opposites attract and there is a positive and negative particle and they are closer together. Okay, so I think there's actually an assumption not stated in here. And I think that might be because they're going to actually attract, they're going to get closer together, so the force is going to get even stronger. I think that's probably what you're assuming, just guessing. And I'm saying that because of what this person said down here at the bottom, and that is B has a larger force because it's forced farther apart than the others. So one of the assumptions that the second two answers we're making is what time are we looking at this situation? Did we already put the particles together and then they move apart? Or have we not let the particles go yet? Does that make sense? So like the person who said that it was letter B because they've been forced further apart, that could be correct if we're looking at this at the end of the force interaction, if that makes sense to everybody, okay? Now, in this case, we are looking at them at the beginning, okay? So we're looking at them at the beginning. So I'm taking the two charges and I'm gonna put them in the little detector, if you will, and then we're gonna let them go. But at the beginning, before we let them go, that's when we're looking at this, okay? So I just put them in, they're sitting there, and they're experiencing a force, and I'm about to let them go, and then the force is gonna do its thing, okay? Now, if we were to take a picture at the end of it, then letter B would actually be correct because it's moved farther apart. It had a greater force. So because of your thinking, that was 100% correct. So I really like that. That was good, okay? So now if we look at it at the beginning of the timeline, and we say at the very beginning, right before I let go of these, what's got the greater force going for it? It's got to be letter A, because they're the closest together. Okay, so now that begs the question that I think everybody's wondering is, what's charge got to do with it? Okay, so let's take a look at what charge has to do with this. So right here we have a positive and a positive. Here we have a negative and a negative. Here we have a positive and a negative and a positive. Okay, so this is Q1, Q2. So we're just going to substitute those in for the equation. So a positive Q1 times a positive is going to equal what? What's a positive times a positive? Tell me in the chat. What's a positive times a positive? Equal. Yes, good. I got a couple answers. Yes, yes. Keep those coming. Positive times a positive is a positive. So it's going to be a positive force. What's a negative times a negative? What's a negative times a negative? A negative times a negative is a positive, right? So we're going to have a positive force for letter B. Okay. What about letter C? We got a positive times a negative. So the answer is going to be a negative force. Well, let's look at this one. What's a negative times a positive? Still a negative. Okay. Now, reaching back to our first unit, or all of our units, what does a negative mean in physics? What do we usually talk about when we talk about negatives in physics? Anybody remember? When we talked about gravity, okay, so we talked about gravity. What did the negative mean when we talked about gravity? We said it's below, it goes down. So that is a direction. We were talking about direction, correct? So anytime in physics or anything, negatives mean direction. So this doesn't tell us how big the force is. It just tells us what direction it's going to happen. So what this means, a positive force means the particles are going to be pushed apart. Positive force means the particles are going to repel. Because look at this, a negative and a negative is still a positive, so they're going to still repel. So the force is positive. A negative force means the particles are going to attract. Okay, so a negative force means the particles are going to attract. A negative force means the particles are going to attract. Okay. So all the negative means is direction. It has nothing to do with how big the force is. It just tells you which way it goes. Okay. So positive and negative has nothing to do with it. So that leaves only distance, because the charges are all the same. If the charges are all the same, the only thing that's changing is the distance here. Okay. So which one has the smaller distance? It's this one. And it's from the center of the charge, from the center of one charge to the center of the other charge. So let's use this straight line here. So look, so that one's way further apart. That one's not too bad, but from the center to the center, this one's still closer. Center to center, oh, that one's pretty close, but this one is still closer together from the center of the charge to the center of the charge. So that means this number on the bottom of the dividing is really small. And if we divide by a small number, then our answer has to be a big number. So this one has the greater force. So the really simple answer is Which one has the greater force? Letter A has the greater force because the charges are closest together. Okay? Now, when I let go of the charges, which one's going to fly apart the fastest? Letter A, because they have the greater force. Okay? Alrighty. So we're going to come back to this idea in a minute, but let's go to try another one. Tell me, which one has the greatest electric force? How do you know? This one should be a little easier, but we'll see. Which one has the greater electric force? So remember what we just said. Does charge have anything to do with how strong the force is? So I'm glad some of you are recognizing opposites attract, like repel, but that has nothing to do with the strength of the force. All that tells us is what direction the force is going to be. You can have a really strong attractive force or a really strong repulsive force. I'm asking which one is the stronger? And it has nothing to do with direction. So positive and negative doesn't matter for this question. All right, let's take a look. All right, B is the correct answer because they are the closest together from the center of the charge to the center of the charge. It's a little harder to tell because they are in different orientations, okay? So they're not exactly in the same, like this one is pretty close, but if I were to actually rotate it, this one is a little bit longer from center to center. This one is further apart. And then this one is the farthest apart. Okay? So biggest force, weakest force. Okay? Charge has nothing to do with it. All the charge is going to tell us is A is going to attract, A is going to repel, B is going to repel, C is going to attract, D is going to attract. Let's take a look at another one. Uh-oh, he changed it up on us. Okay? You smell bacon and rice? Okay. My daughter's joining me for breakfast. All right. So which one's the greatest? A, B, or C? The assumption we're making is, and it doesn't look like it, but the distance from center to center is the same for all of these. So the distance is the same for all of them. Doesn't look like it, but the distance is the same for all of them. So now which one is going to have the greatest force? Okay, so the size of the objects here is representing the amount of charge that object has. So that might clarify some things for you. If we're talking like an actual metal conductor, the metal plate doesn't change, but it could still have a much larger charge than another piece of metal. So I know there's a little bit of a falsity to what we're showing you here, but it was the easiest way to show you that the charge on one is bigger than the charge on the other. So I just made the circles bigger. So the bigger the circle, the bigger the charge. The smaller the circle, the smaller the charge. I hope that I should have said that at the beginning. So now which one has the greater force? Should be letter D. Why? So the distance isn't changing, but we have a really big Q1, we have a really big Q2. So a big number times a big number is going to equal a bigger number. Okay, so if I take a big number, Q1 times a big number, Q2, it's going to equal a bigger number for the force. Okay. This one's going to be the smallest force because we have a small force, I mean a small charge times a small charge, and so we're going to get only a little bit bigger force, okay? Actually, I shouldn't draw those arrows that way, because it's actually big times, I mean small times small equals a little bit bigger. Yeah, that would be confusing. Whereas down here we have bigger arrow times bigger arrow, and so we get a bigger result. So these are called directly proportional. So as one gets bigger, the other one also matches it. It gets bigger as well. Whereas if the distances are changing, the distance gets bigger, the answer gets smaller. That's called inversely proportional. It's opposite. All right. So let's see. All right, we'll come to that in a second. So a couple things to think about here. So what happens when I put two positives together in the nucleus of an atom? So we look at the atom in the nucleus of an atom, and I put two positives, two protons together. What should happen? Based on what you know, tell me in the chat, what should happen if I put two protons next to each other? What should happen? Good, I'm getting several private messages telling me. Go ahead and tell me what happens when I put two positive charges together. Yep. Good answers. The answer will be positive, but then what direction will the charges move? Okay. The force would be positive, but which direction do they move? Good. Using the correct language, they repel. So they should repel. Now, let's think about this though. If I have a hydrogen, a helium atom, which has two protons, the nucleus doesn't fall apart. Those protons don't split from each other. So why? So why don't the two protons split apart in the nucleus of an atom? Okay, and that's a major question scientists had when we were figuring this out, and it led us to these things: the strong nuclear force, the weak nuclear force, and gravity. The only reason they don't repel, because there is an electric force pushing them apart, trying to make them repel. So why don't they fly apart? Because there's another force holding them still. Okay? So it's just like you put a book on a table. Well, there's gravity pushing down, but the table's pushing back up, so the book doesn't go anywhere. So there's an electric force pulling them apart, but there's a strong nuclear force also holding them together. And the strong nuclear force is stronger, so they stay stuck together. Okay? So there are other forces involved. What you need to know is gravity is so much weaker than the electric force, it almost has no impact in the nucleus of the atom. It has to be this strong nuclear force which holds them together. And it does, okay? The weak nuclear force is also at work. So there's two other forces that we're not gonna talk a whole lot about in this class because we won't have time. But there are four fundamental forces in nature. There's the strong nuclear force, weak nuclear force, and the electromagnetic force. Okay? And this one, and this one have all been unified with string theory. Okay? So the nuclear force holds the protons together so they don't fly apart. They are being repelled by the electromagnetic force. It's just that the strong nuclear force is stronger. So we have, let me draw this. This will help. So we have, let me pick a different color. So we have our electromagnetic force. Electromagnetic force. but we also have our strong nuclear force holding them together. And the strong nuclear force is stronger. So there's two forces acting, and one of them is stronger until they stick together. Okay? Like if I'm holding my cup, okay, which you can't see because of the green screen stuff. If I'm holding my cup, gravity's pulling it down, but my hand is holding it up. So why doesn't it fall? Because there's another force keeping it from falling. Okay? So sometimes we lose sight of that when we get into this, that, you know, the world is a lot more complicated than just, oh, we got one force. Okay? So keep that in mind. All right. I wish we could talk more about that because this is really fascinating how this all works. But we need to move on. All right. So in Canvas, let's take a look in Canvas and at our work for today. I've already explained some of this in our weekly overview video. Be careful. This one, there's actually a mistake. It says the same thing twice. So you actually have the same answer written twice. So be careful of that. When you get to the balloon gizmo, it's actually pretty simple. You just click and drag, okay? And you can click and drag, and then you can let go. You can do 2 balloons. You can reset the balloons. Okay? You can reset the balloons, but you can also reset the whole thing. Okay? You can show no charge, show charge difference. Okay? You can remove the wall. You can do all kinds of stuff, but then you can hit reset. When it's time to draw the picture, I could draw the picture much faster on paper. So I would draw it on paper and then take a picture. However, before you do that, know that down here, you're going to do another picture. So what I would do is you're going to draw the before. What is the balloon, the charge on the balloon and the sweater before? And then you're going to draw the sweater and balloon after. So I would draw those first, and then I would put in the picture after. If you want to do a screenshot, that's fine. But there's something to drawing it by hand as well. So either one. You can also use the drawing tool. So you can go to insert image and insert your picture from your phone, but you can also insert the drawing. It's just the drawing can be almost more complicated than doing a screenshot or whatever, but you can insert. And here's my sweater shape. I'll use that for my sweater. And then I can put in my charges, put in my circles for charges. You can do it that way too, but that's pretty complicated actually. And then you can just double click on it and type and put in your charges. You have to change the color of the font, which is over here. Change that to yellow. So I got my positive or whatever. And then you just save and close, and it puts the drawing in your deal. It's probably easier to do it by hand and take a picture or take a screenshot. Okay? If you're doing screenshots, you need to do it right away. If you're doing it by hand, you can draw both pictures and then just take one picture with your phone and then insert the one picture. All right, read it carefully. This one, the John Travoltage, is really simple. You just drag his foot and you can move his hand. Okay? Be sure you're reading the directions carefully. When you get to this bottom one, this one can be confusing. I've included very detailed instructions with lots of pictures explaining what each thing is. So please read carefully, okay? Just know that the cool part about this simulation is reset is your friend. You can drag out positives, and then checking what you need is important. Okay, so here's field lines. They all go away from the positive. They go towards the negative. Okay, we put positive and negative together. You can see the field line. You can also show the voltage. So like a 12-volt battery, okay, has to do with positive and negative charge and how it works. And this is actually drawing the equipotential, which is essentially the precursor before we learn about voltage, okay? So you can map out a series of charges. You can also click the erase button. Okay, and I'm going fast because most of this is explained in the video. I mean in the document. And then you can turn on values and it will tell you what the voltage actually is, okay? And I know you don't understand some of that exactly, but I still want you to work with it because when we talk about voltage next week, it'll make a lot more sense having played around with it a little bit before we talk about it, okay? So read those directions carefully, and I think you'll figure out most of it. Okay, it's actually pretty simple overall. What I want you to do, you have two sets of particles here. Basically, you're going to answer this question, and then you have the remaining 25 minutes of class to work on whatever you need to work on. Okay, so which set of particles has experiencing the greater force? Explain why you say so. If you don't have enough information to answer the question, then you need to tell me what information you need. Okay, so this is about your explanation. There's not necessarily a right or wrong answer. So, but you got to be able to explain and defend your answer. So answer that question in the Pear Deck and begin working on either the PhET simulation or any other missing work, and I will hang out. We will hang out and work together for about the next 23 minutes. And at the end of class, we'll talk about the answer to this question. Great explanations for the answers you're putting. Continue to put those down and be working on stuff. Okay, so let's take a look at this. It probably would be B because the pair is further. Even if it's larger in size, it might not have a greater electric force. I don't really know because it could be A because the size indicates they have more charge, whereas for B, they are closer together, so we don't know. I think B will have the greater force because although it has a small size, it has a smaller distance. I think distance has more impact on the force, which is true in general. And then I like this one. It can't be solved as the variables may cancel each other out, possibly making them equal, which is also true. So all of those statements I really liked because it showed your thinking and that you're thinking through Coulomb's law. The bigger the charge, the bigger the force, but the closer they are, the bigger the force. And without actual numbers, we can't know for sure which one is bigger. So great thinking. Thank you for sharing. If you have any questions, please stick around and I will see you next week.